All right, so we were kind of going over last time kind of how we can have different types of compounds, how molecules can kind of come together in a few different ways to either make molecules that are more what we'd call like the molecular compounds or molecules that are more what we'd call ionic compounds. And the difference between those is kind of what atoms come together. And the reason the atoms behave a little bit differently on the metals versus the non-metals is mostly due to where those atoms are in terms of what their electrons look like, how big they are, how small they are, how structured they are in that regard. So really, really big atoms, those are the atoms kind of, if we were looking at a periodic table, are going to be over on this side here, the metal side versus the not metal side over there. So the metal side of the periodic table, those are on the left side generally. They're going to be the bigger atoms, especially as you get down into this bottom left corner here. Those are the atoms that are particularly good size. And because they're very large atoms, they have what's called a low electronegativity. They don't really like having electrons. They want to give away electrons. They have a low ionization energy. That means it's actually really easy to take electrons from them too. And because of that, those generally tend to form atoms that give away their electrons. They generally become something that's positive. So they're going to give away one electron if they're in the first column, 2 electrons if they're in the second. They'll give away numerous other electrons too, and you can kind of predict that charge based on where they are. And whenever you pair one of those up with something, it's going to try to give those electrons away. And it's going to give those to something that wants it from over here on the non-metal side. So the atoms over on the non-metal side, those are the ones that are going to be smaller atoms. They have small nucleus, and they're able to hold on to their electrons really well. They're able to hold on to their electrons, so it's really hard to take them away. That means it's a high ionization energy versus a low ionization energy. It's easy to lose an electron. These are really hard to take electrons. And they actually have a high electronegativity too, that not only do they like having their electrons, they like grabbing other atoms' electrons too. So they're either going to share electrons with other atoms of that type. So you may have something like a chlorine sharing with another chlorine and forming a bond, or you'll have a chlorine that'll actually take away the electron from some other atom, and it will become positive over here and negative over there. So the non-metal atoms, if they're paired up with other non-metals, they're going to form one type of bond. And if they're paired up with the metals, they'll form a different type of bond. So when metals and non-metals come together, we get these ionic compounds. Those are things where one atom gives away the electron, one atom takes the electron, versus if you have 2 non-metals or more than 2 non-metals, but at least 2 non-metals, coming together, then they're going to start sharing electrons because they're both going to try to take from each other, essentially. You have one chlorine that's trying to take an electron and another chlorine that's also trying to take an electron. And you end up with a bond between those two because they're both trying to grab onto that electron at the same time. They end up sharing it. Versus over here, one takes it from the other one. And that's kind of the difference between those. And it's, again, if you have a metal in it or not. So if you have 2 non-metals, you have a molecular compound, we'll do those Lewis dot structures, we'll do the dots, we'll see how things come together, either sharing 2 electrons, maybe sharing 4, maybe even sharing 6, versus the metals and the non-metals are going to not share. They're going to take from one, give to the other for those. So they're not sharing there. And you can kind of predict what it is by just kind of looking at the periodic table, right? See, are you on the metal versus the not metal side of the periodic table? So the metals are all on the left, non-metals are over here on the right. There's a little staircasey looking thing here that kind of helps divide a little bit too to help you remember that. But also, if you do have a bunch of metals, you could figure out what charge they are, right? The first column here, these are all going to be +1 charge. Second column here, +2. If you're in this third column here, you'll form ions with a +3. And then from the other side over there, we could figure out, the charge of those if we needed to. The first column on the left doesn't really need anything, but as you go farther and farther over, they're going to become more and more negative. And then you can also do things like the dot structures, but you can kind of see how this one is one shot. It has 7 out of 8. It only needs 1 more electron to get to 8, so it's going to grab that and become -1 charged. And then they'll keep going kind of further along there. And we had kind of talked about that a little bit. We talked about how the ions sometimes have special names, but you could also just call it a negative ion or a positive ion. But generally, right, the metals, these are over on the right side there, they have positive charges. The nonmetals, negative charges. And you can even kind of look at it by looking at the table and seeing kind of where they are. So if you have an atom in that first column, +1, second column, third column, so you can kind of predict those charges when you do have them paired up. If you had a metal with a non-metal, what ion is going to form positive atom, what atom is going to form a negative ion. We can kind of see how they both switch between each other. And sometimes it's hard to predict. So if it's anywhere else, they'd have to tell you. But if it's anywhere from those first 3 columns or last 3 columns, we can kind of tell from that. And then we kind of showed a few examples where we did this for some different atoms. And I'll leave this one up. So this was one more. I guess we'll do that one now. So this was just talking about with the strontium, right? So different atoms, depending on where you are, you could figure out what that atom is. So let's put this here for a second so I don't forget. So kind of just like we said before with like things like the lithium or the potassium from the previous example, right? We checked and saw, oh, it's in this column here. It's got a +1 versus like the oxygen was over in this column here. So you can count the dots, right? Oxygen would have 1, 2, 3, 4, 5, 6 dots out of 8. So oxygen has 6 out of 8. It wants to get to 8. So if it could get 2 more electrons, it would be a negative, it would be 8 total. And that puts it in the -2 if we're counting 1, 2. This is 0 because these already have 8 dots. These are 1 dot short or 2 dots short. So we can kind of do that for any atom that we wanted to. So if you want to do it for like the P or the N, right, that would be a -3 charge. If we were looking over on the beryllium Mg side, right, those would be +2 or a +1. So it's just kind of the idea of kind of looking at an atom, where it is on the periodic table. So Sr is down here. So you can kind of figure out what column that is in and kind of what charge you would expect for an atom of that charge for there. So that was kind of an example of kind of looking at things like that, like figuring out what the charges of atoms are going to be. And it's all based on those dots and based on those kind of positions in the periodic table. And we know because it's in the purple side, the metal side on the right here, left here, that it's going to be positive versus the atoms over on the left side over here generally form negatives because they're trying to gain more electrons versus these ones are trying to give away their electrons. If you're trying to give away electrons, you're going to become more positive. If you're taking electrons, you're going to become more negative. So depending on which way you go, you can either become more or less positive or more or less negative. And good, yep, a lot of people put 2+ or +2, so those were good. So a lot of people got that kind of idea right. And again, because we're on the right side over here, we're on the giving away electrons. So potassium or Rb here, these are going to give away 1. Ca, Sr, Mg, Ba, these are all going to give away 2. So they'll go to +1 first, and that's still not 8, so they'll go to +2. They'll keep giving away until they get to the right spot. But a lot of people got that done, so that was good. And when you do this, right, you can form these molecules. So you're trying to form these molecules, trying to form these structures, which is what we're kind of going through at the end. And they form compounds. So if you have something that has a -2 charge, like that oxygen, or something like this Ca, right, this oxygen here, right, it's got 6 electrons. And if it can put 2 more electrons in this spot right here, it'll be really happy. It'll go from having 6 to having 8. So it does that. It goes around until it finds 2 more electrons. So it found 2 more electrons, became a -2 charged oxygen. But it had to get those electrons from somewhere. And it gets them because oxygen's, again, on the left side of the periodic, right side of the periodic table over here. It's a nonmetal. It's going to be getting its electrons from either sharing with other nonmetals, or in the case of ionic compounds, from taking from metals, like calcium. Calcium's a metal. Calcium's over here. It's on the +2 side. And calcium's got these 2 electrons that it really doesn't want to have. So it's going to try to give them away as soon as it can. And as soon as it gives away 1 electron, it becomes +1. Gives away 2 electrons, becomes +2. And you see there's no dots around it, but that's okay. Having 0 dots is just as good as having 8 dots. So both of these atoms are happy now. One atom's got a +2, one atom's got a -2, but they both got their 8 dots. Or no dots. Again, 8 dots and 0 dots are both okay. So we get these 2 atoms. And if you have a calcium with a +2, it's going to be attracted to anything that's negative. and an oxygen with a -2 is going to attract that really well, and you form a compound, CaO. So CaO is an ionic compound. We could write its formula out. We would just write it out as Ca and O. And on this ionic compound, one had a +2, one had a -2, but if you add +2 and -2 together, you get 0, right? 2 +2 -2 goes to 0. So the overall charge of this molecule is 0, and that's what we want to have. Whenever we have an ionic compound, they should have an overall 0 charge. So you always want to have a charge of 0 on that compound. So this one here worked out really well. +2 from the calcium, -2 from the oxygen, we're good right there. But if we had something else like this sodium, Na+, right? Na is also going to give away electrons. So this sodium here wants to give away an electron. It gives away 1 electron, becomes Na+. So if we took calcium and we mixed it with oxygen and sodium, we could put oxygen and sodium together too, and you would have, right, O2- and Na+. And if those came together to make NaO, we would have a +1 and a -2. We'd have an overall -1 charge. So that's not going to work, right? We have to have an overall charge of 0, but we can get to that still, because rather than having 1 sodium with a +1, what if we put in 2? We could have 2 sodiums here. So we'll put another sodium there, and now you have 2 +1s and a -2, and now it does equal 0. So we have 2 +1s and a -2, and that gives us an overall 0 charge. So rather than having NaO, you'd have Na2O. You have 2 sodiums, 1 oxygen, and an overall 0 charge. So for these molecules, whenever you're working with ionic compounds, again, something on the right side of the periodic table like calcium, something on the right side of the periodic table like sodium, Na, and something on the left side like this O-, as long as you have the right charges, that everything balances out to 0. So for every plus you have a minus, or if you have 2 pluses, maybe you have 2 minuses, or 3 pluses, you need 3 minuses. You can rearrange those atoms in such a way that everything comes to 0. So if you have 2 that are, +2 -2, no problem, they go together. +1 -1, they go together. +2, we need 2 minuses, so either a -2 or 2 +1s. Those will both go to 2 together. So we can kind of mix and match. So here we had +2 -2, no problem. Here we had -2 and 2 +1s. That's also going to work to cancel things out. So when you see these ionic compounds, you can actually look at the formula and figure out the charges of those atoms. Or if you know the charges of those atoms, you can figure out what formula you need to get an overall 0 charge. And this works with negatives too, just like with the, like we had with the positives here, right? So Cl has a -1 charge. We already said that Ca is a +2. So if you had Ca and Cl together, right? Ca and Cl, right? This is +2. This is -1. So if we want to cancel out all the pluses with all the minuses, we're going to need 2 of these. We're going to need 2 Cls so that it becomes 2 times -1. So that would be Ca and then Cl, and we'll put the little 2 there because now there's 2 -1s interacting with 1 +2. So that would work. Versus if you had something like Na, Na is a +1. And then Cl is a -1. So you can just put Na and Cl together because +1, -1 cancel out. We don't need any extra Cls or any extra Nas. 1 and 1 work together for there. So always look at your charge. And again, you can always figure out the charge by going on the table and figuring out kind of how far over you are. So as you kind of go the +1 column, the +2 column, and then you keep going, right? Calcium's in the +2 column. Na is in the +1 column, Cl is over on the other side in the -1 column. And by looking at those different columns, we can figure out how positive or how negative everything is. And when we see things that are very negative or very positive, we can kind of cancel them out. So if we have +1, we're going to need 2 of those. Over here, right, +2 and 2 -1s versus a +1 and a -1, or a 2 and a 1, Or even things like 3 may have other kind of more exotic compounds. Maybe you have one thing that's a +3 and something that's a -2, right? You may have to kind of get creative with how you mix and match things so that everything cancels out with all your charges there. But overall, it's going to come to 0. You'll pair up all your positives and all your negatives in such a way that things come out to be overall 0 on the molecule. And this was just kind of one, so this will kind of be an example here. So this was looking at kind of ionic versus molecular compounds, right? So some compounds form more ionic compounds. If you have 2 nonmetals, they're going to be molecular. If you have a metal and a nonmetal, you'll be more ionic. And this was basically just asking, right? So if we look here, it's saying, what's an ionic compound with oxygen? Well, oxygen itself is on the right side. Oxygen's a green box. Those are all the nonmetals. 2 nonmetals are going to form molecular compounds, and a nonmetal metal is going to form an ionic compound. So since oxygen is a nonmetal, it's going to form an ionic compound with a metal. So this question's just asking which of these atoms is a metal, is another way to kind of ask that question. So sometimes it's just a really easy question, but they didn't want to ask it that way, so they kind of word it in such a way to make it a little bit more complicated. But this is just asking, right, which of these atoms is a metal? Which of these atoms is on the left side of the periodic table versus the right side of the table? So carbon, carbon C, so we can move this up, give everybody a little bit more time. Right, so carbon C, it's all the way over there. Let's see, can we fit everybody? We can fit a few of them, right? So carbon's up on the top corner, it's green. That's a metal compound, or non-metal compound. Also have things like calcium, right? Calcium's over here. Phosphorus was P. One more time. So as you kind of go down that list, right, you'll see some are metals and some are non-metals, and ideally only one of these is a metal, the other ones are the non-metals, but that's what you can ask, right? You can think about, what atoms am I working with? Am I working with a metal and a non-metal? That's a metallic or an ionic compound. Am I working with a metal, 2 non-metals? That's a molecular compound or a covalent compound. So that was kind of a way of looking at things like that. Again, yeah, most people got the calcium going there, so doing good with that. Skip. Now we'll skip that one. We'll leave this one just to kind of think about it for a second. So for this one, right, this was just kind of a numbery question, but it was doing with compounds, right? You have to have an overall 0 charge. So if we had something like sulfur, where we had a -2, we would go back to that other table. You'd see that sulfur was in the same row as oxygen. It's got a -2 going on with it. And other atoms, right, if you pair sulfur, which is a nonmetal, with a metal, you would get an ionic compound. And the big rule for ionic compounds is there's overall a 0 charge. So everything is negative and everything is positive, got to cancel each other out. So if we have something that's -2 and we have something that's +4, we want to have an overall 0 charge. And right now, -2 plus 4 gives you an overall +2, because the +4 and the -2 don't quite cancel out. But if you had multiple of these -2 compounds, you actually could cancel out, right? So if you had 1 -2, you'd be at -2. If you had 2 -2s, you'd be at -4. If you had 3 -2s, you'd be at -6. And that would let you cancel out with that +4 there. So that would be kind of like looking at a formula of a molecule. So this would be S something, Fe, or iron something. So it's a way of kind of looking at those molecules. And again, we can figure out the formula for ionic compounds because we know that all those pluses and all those minuses got to cancel out with each other. And in this case here, right, if we have a +4, we need a -4. And we can get -4 by taking 2 of these -2s, right? 1 -2 is 2. 2 -2s would be -4. So the 2 -4s and the +4 would cancel out with each other. So you can actually make a molecule that would work for that. So that was kind of what we were looking at. Most people got 2 there, so great. So that's kind of that idea of looking at molecules coming together and figuring out the formulas for those. So just jump back to our periodic table again. So we're always going to make sure our pluses and our minuses cancel out. if we have one of each. But we can also have just no metals involved at all. We can also have just nonmetals. So nonmetals are always going to form bonds, and they'll either form bonds with metals or with themselves. So the nonmetals are very versatile. They'll bond with a metal if it's there. They'll take some electrons, become positive and negative, or they'll just hang out with themselves and hook up with the other atoms that are in the nonmetal section. So nonmetals will bind to either one. And kind of just checking when you have a formula, is it a metal-nonmetal pair or is it a non-metal-nonmetal pair? Because you can have either these ionic compounds, or we can get back to that idea of covalent molecules. Again, two nonmetals now. And nonmetals, when they come together, they can form bonds too. Like we'd said earlier, nonmetals can form bonds with other nonmetals. And it's when they share electrons. But some atoms are pretty good at sharing, like these two hydrogens right here. These two hydrogens are sharing this pair of electrons. So we got two electrons here, and these hydrogens are sharing it, right? If you were to do a Lewis dot diagram for a hydrogen, hydrogen has one dot. Another hydrogen comes in, it's also got a dot. So these hydrogens end up sharing this pair of electrons so that they form a bond. And you could draw the bond as just H with a dash between them. So that's our pair of hydrogens here sharing an electron, and you can see these little rodeo guys sharing their electrons pretty evenly, right? If you measured this distance, and we can tell the distance here by looking at how much rope there is, right? So these guys are each holding onto this rope, and they're holding about the same distance. Maybe they got like 2 hands worth of rope between the two of them, one on each side. They're sharing this really evenly. So this would be like if you have a sibling and you have a twin or a sibling who's about the same age as you, and you both want the same toy, and you both grab onto it, and nothing's going to happen. You have about the same strength. One of you pulls, the other pulls. You're holding onto that same toy, and actually, you know, you can just come along, you can grab the toy and move both of you because there's this bond between the two of you, the toy that you're both trying to snatch from each other. Or if you have two dogs, especially if you have little tiny barky dogs, they both go for the same toy, and when you need to move them, you just grab the toy, and both dogs come up with you because they're both hanging onto that toy, and they've bonded each other. Just like these hydrogens here formed a bond. But some atoms are a little bit bigger, a little bit stronger, and they pull a little bit more strongly. So if you have an older sibling, or if you are the older sibling, and you want that toy, maybe you can pull with a little bit more force. And the littler sibling is still going to hang on, but they're not able to hang on as well, and the toy is spending a little bit more time with you. And we see that happen with atoms as well. We see that happen with other nonmetals. Chlorine is also a nonmetal. So these are still two nonmetals. Chlorine's a nonmetal as well as hydrogen. But chlorine is a little bit stronger on pulling on those electrons. And we can see that it's pulled a lot more of the electron closer. And the distance over here is much larger than the distance to over here. So chlorine, if we're kind of looking at the electrons, had one dot. Hydrogen had one dot. But hydrogen's dot is spending a little bit more time over with the chlorine than it is with itself. And that's because this is what we'd call a polar compound. So polar compounds arise when you have two nonmetals, but they're two nonmetals that don't share the electron equally. So a polar covalent bond is still two nonmetals, but they're two nonmetals that aren't sharing their electrons as well. So these two hydrogens are two nonmetals, and they share really well. They're good sharers. This chlorine is not so good a sharer. It's a little bit more of a taker, but the hydrogen's not able to let go entirely. So it's not like if you had like a nonmetal here, a nonmetal would have said, fine, you want those electrons, you can have them. I didn't want them anyway. I'm going to go do something else now. And the hydrogen's like, no, I really, really, really need those electrons, but you're really strong, but I'm going to hang on as much as I can. So this hydrogen's hanging on as strong as it can. It's not very good at holding on, but it's still holding on. It hasn't let go of the electrons, unlike a metal. So it's different than when you have a metal-non-metal pair. Neither one of these becomes positive completely or negative completely, but this chlorine is a little bit more negative. And they'll show that by putting a little negative sign with a little D-looking shape or a music note shape. And that's letting you know that this chlorine is a little bit more negative than the average chlorine. So you could have regular chlorine that has a 0 charge. You could have chlorine with a negative charge. And you could have chlorine with this little sign here that's somewhere in between. It's not totally negative, it's not totally neutral, but it's somewhere between the two of them. And if you ever see these little delta signs or these little music note shaped things, they kind of look like a lowercase d with or maybe a figure eight that somebody didn't quite draw all the way. These are ways of letting you know that this atom's a little bit negative. So this is sort of negative. So it's not totally neutral, it's not totally negative, it's kind of negative, it's a little bit negative. And that's because this chlorine here is pulling away some of the electrons from the hydrogen. Hydrogen's a tiny bit positive, but not 100% positive one. Chlorine's a little bit negative. And that's going to impact some of the chemistries of these atoms when we start to do other chemical reactions. It's going to make these atoms behave a little bit differently if we try to react them with each other. It's going to make them stick to other things when we do molecules with this. It's going to help proteins stick together. It's going to help in a lot of biochemical properties. It's going to help with drugs. These partial negative charges help drugs bind to other drugs, helps your body send signals to other parts of the body. It's very important to have that versus these non-interacting charges here, but that happens quite a bit. Basically, this happens whenever you have two atoms that are sharing electrons that aren't the same atom. So if you have two hydrogens, they pull the same, they're identical. But if you have a hydrogen with a chlorine, or a chlorine with a fluorine, or a sodium with a fluorine, those are all going to be atoms that are unequal. And when the atoms aren't equal, one of them generally pulls a little bit more than the other. So whenever you have two nonmetals that are different than each other, one of them is probably going to hog the electron a little bit more than the other one does. So that's kind of this idea of atoms not sharing electrons, and that does have some impact on the shape that these molecules actually take. So when we draw like things like water, right, you can write H2O, but you could also kind of draw water molecules, and we usually draw them as this kind of Mickey Mouse shape molecule, where you have two hydrogens up here and the oxygen down here, and we don't draw it like this. We don't draw them as a straight line, we draw it as this kind of bent shape here. And molecules actually have very specific shapes, and we can figure out the shapes of those molecules because that has impacts, again, with how they behave as drugs, how they behave in biology. But to be able to know that water looks like this and not like this relies on the electrons, and it relies on how those atoms come together. And you can only do this for atoms that are molecules. So if you do this for molecules that are covalent, so molecules with covalent bonds, we can do this. And it has to do with the electrons basically trying to stay away from each other and putting themselves into the right shapes. So we can't do this for metal plus a non-metal. So if you do it for an ionic compound, we don't do this. But if you do have two nonmetals or more, so 2 plus nonmetals, then we can actually figure out the shape of the molecule. So if you have 3 nonmetals, 4 nonmetals, any kind of multiple nonmetals, so again, all those green atoms on the right side of the periodic table, those can help us figure out what the shape of that molecule is. And the shapes of those molecules has impact on their polarity, has impact on how well they serve as drugs, has a lot of impact on the nature of that molecule there. And atoms, again, we're working with this. This is the molecular compounds we're working with. So molecular compounds are kind of neat. They're the ones that can have double, single, triple bonds. They're the ones we're going to do the Lewis dot structures of. And they're the ones that actually will also figure out the shape of. So we don't have to worry about shapes of ionic compounds. We don't have to worry about double and single bonds in ionic compounds. We only have to worry about that when you have 2 nonmetals or more nonmetals. So when you have only nonmetals in that molecule. And there's pretty much 3 types of shapes that can exist in these molecules. And it has to do with kind of keeping things as far apart from each other as possible. So if you had 2 things and you wanted to keep 2 different things, so your molecules as far apart from each other as possible, well, you can just put them too far apart from each other, 2 units away from each other. And if you had 3 things and your head was one thing and your 2 hands were each other, and you want your 2 hands as far apart from each other and your head, you wouldn't put them like this. You wouldn't put them like this. You'd put them here and here. And now this hand is as far apart from this hand and my head as possible. And that's what you get when you have atoms that are kind of what we call linear atoms. So something like a carbon bonded to maybe a nitrogen, and another nitrogen like that. And depending on how we get the bonds, there's probably some double bonds going on here as well. So this would be an atom where the central atom and the other atoms are as far apart from each other as possible. But when we start adding in more and more atoms, we're going to start having a problem with that. So if we had 4 atoms, so we have 1 atom in the middle, and then we have atoms 2, 3, and 4. Again, we want those atoms as far apart from each other as possible. So 2 atoms, no problem here. I'll throw in a 3rd atom that I'll put here, so I can put all 3 on top of each other. That's not very good because they're close to me and each other. All right, well, I'll put this one here and this one here, and you can kind of basically go to a triangle shape. So this atom, and this atom are as far apart from each other as possible, and they can't really get any closer. And that makes sense. It's 4. And then when you go and add a 5th, you could just make a square. And squares are pretty far apart from each other, right? If you think about the points of a square, you could have 1, 2, 3, 4. Those are pretty far apart from each other, but that's only thinking in 2 dimensions. And if you think in 3 dimensions instead, so you can do this with like your fingers. You have 2 fingers and 2 fingers, right? You can put those 4 fingers in a square like that. That's pretty far apart. But if instead you put your fingers like this, you can have 1 finger up here, 1 finger all the way down here, and the other 2 out in the 2 planes of the other way. And that's even further apart from each other. Or do this at home, get 4 balls or 4 things that you can stack, right? You can put 4 balls in a flat square, that's good. But if you actually put 1 ball on top of the other 3 and measure this distance to this distance versus doing it the other way, it's actually further apart to have 1 stacked and then a triangle. So this is kind of a way of, again, maximizing space. We want to get these things as far apart from each other as we can. So this distance, this distance, this distance. So we're trying to make everything as far apart from each other as possible, and you get this kind of shape here. So depending on how many atoms are in your molecule, so something like this would be if you had a carbon, for instance, and you had a bunch of fluorines hanging out with that carbon. So we have 4 fluorines hanging out with that carbon. We do our Lewis dot structure. We get a bunch of bonds there. So there's going to be a bunch of bonds holding those carbons and fluorines together. So we'll do that. So that's kind of a shape we may get versus something if we had 1 atom with 3 atoms around it, or 1 atom and 2 pairs. So depending on what kind of molecule you're getting or how many atoms are involved, so maybe this is an oxygen, carbon, and then 2 hydrogens here. And we have some double bonds. So you may have something like that. So you get all these different molecules that have different shapes. And these different shapes are partly due to how many atoms are involved, right? This one's only got 3 atoms total. This one's got 4. This one's got 5. So the number of atoms involved is going to change the shape of that molecule, but also the bonding and the polarity is going to change the shape. But it's going to fall into one of these kind of 3 main categories. And we can kind of figure that out by kind of looking at the atoms themselves. This is just kind of showing those same categories again, but from kind of a more different perspective, right? So if you had the atom in the middle, 1 atom on the edge, so you have 1 atom in the middle here, and then 1 on either side, or 1 atom in the middle here, and 1, 2, 3 things connected to it, or 1 atom in the middle, and 1, 2, 3, 4 things. So depending on how many things are on your atom, which is the atom in the middle that we're not going to count, we can get a couple different shapes. And these different shapes will arise from how many different atoms are present around that central atom. So if you have 1 atom with 2 things around it, you'll get a certain shape. And this is what we call a linear shape. So this is what we call a linear atom because everything is in a straight line, right? Atom 1, atom 2, and the middle atom are all lined up straight with each other. Versus if you have 3 atoms around a central atom that look like a triangle, this is a trigonal planar atom. So it looks like a triangle and it's a plane. So this is a trigonal planar. And that's different than this what's called a trigonal pyramid. So this is a triangle too, but it's a triangle pyramid. And if anybody plays D&D or any games, this is a D4. This is a 4-sided dice, right? 4 sides on a face there. So there's different ways of putting molecules into different shapes. And again, we're keeping these atoms as far apart from each other as possible. So by having these atoms as far apart from each other as possible, we produce different shapes and different patterns, and the molecules are going to behave a little bit differently because a flat triangle-shaped molecule may be able to fit into places that a triangle planar that's three-dimensional can't. Or a linear molecule may be able to fit through a hole that this triangle can't fit through. So it's going to change the shape of the molecule, may change its behaviors in chemistry, different reactions that can occur, different attractive forces that can occur with these different atoms based on the shape. But we can kind of look at it and look at the molecules. So when you do your Lewis dot structures and you say, all right, well, how many atoms are around my central atom here? What shape is my molecule? So if you had something like O and two C's, it may be linear. If you had something like a C with three things around it or four things around it, it may be trigonal planar or trigonal pyramid. So these are kind of some examples, right? So we did some Lewis dot structures. We took a nitrogen. Nitrogen, if you look on the periodic table, is supposed to have 5 dots around it. Hydrogen's supposed to have 1. Carbon's supposed to have 4. And we do our structure, and you get something that kind of looks like this. Hydrogen has a single bond to the nitrogen has a triple bond to the carbon, and the carbon has 2 dots on its own. And this is our kind of final structure for that particular molecule after we went through and did all the dots and did all the counting. And then there was an extra electron here from being negatively charged. So this is our atom right here, and you can kind of draw it either way there, but that's a kind of Lewis dot structure for that. And after you did your Lewis dot structure, you looked at all the atoms that are involved and the positions of all those atoms, and it asks you what kind of shape is this molecule. Well, you could do that too. You could figure that out after you've drawn this Lewis dot structure. You would just kind of say, all right, well, how many atoms do I have? I have 1 atom in the middle, and then I have 1 atom on the side, and another atom over here. I have 2 atoms that are in a straight line with a central atom. This looks like a linear type of molecule. And that's how you can kind of check that. So linear molecules, 1 central atom, 2 atoms on either side, 1 to the left, 1 to the right, 180-degree bond length. So it's a straight line, right? The distance from here to here in terms of angles is 180 degrees. So they're nice and spaced out from each other. So that's a way of kind of looking at those atoms. And this is going to be a flat molecule. It's going to be a linear molecule. It's like a pencil. So this molecule has certain behaviors that other atoms aren't going to have. And you could do that when you're doing the Lewis dot structures for any of these types of atoms. We could do this for this other molecule too. We would look on our periodic table. Oxygen is in the 6 dot club. So oxygen's supposed to have 6 dots. Carbon's supposed to have 4. Hydrogens have 1. And there's 2 of them. So we should have 12 dots total. And we could do the Lewis dot structure for this molecule here. We'll put a carbon here. We'll put the 2 hydrogens in place and the oxygen. And then we just start filling in things. So hydrogen, connect the dots here. Hydrogen, connect the dots here. Oxygen, connect the dots. And we end up with something that looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 dots. So this is a 12 dot structure. It's got the right number of dots. We did it right. And if we were to look at this atom here, it's a big triangle, right? It's got a oxygen, hydrogen, hydrogen, oxygen. So this is a triangle planar molecule here. And it's a little bit bigger than this linear molecule. It's got this other piece sticking off. But we could do this for any atom we want to work with. This is, again, flat. Both of these molecules are flat. One of them has 3 things, one of them has 2 things, but they're both flat molecules. These atoms are 180 apart. These atoms, the distance from hydrogen to oxygen here is about 120 degrees. So this would be a 120-degree angle here. And then so would this, and so would that. So you could look at the angles of these atoms if you needed to. You could look at the shape or how flat these molecules are if you needed to. And we could measure those things as well. And you would say that this atom's trigonal planar and the other atom's linear. So when we're doing our Lewis dots, we can always figure out what kind of shape our molecule has. And we could even do it for this one here, this CH4 molecule. You'd have a carbon in the middle. You'd have 2 hydrogens kind of sticking out to the front. I'm kind of going to try to draw it sort of 3D shape. This one's sticking up. And then this one's kind of sticking behind it. So this is kind of like an umbrella. So like when your umbrella flips inside out on a windy day, the umbrella gets flipped inside out. The 3 hydrogens are along the inside out part of the umbrella. And the other hydrogen is the handle. And the carbon is where all the metal pieces come together there. So that's kind of our 3-dimensional shape of this atom too. But now this atom is actually three-dimensional. It has a piece sticking up, it has some pieces sticking out to the sides. It's actually 3D, versus these two are both flat. So one's flat, one's linear, one's a line, one's a flat plane, and one goes out in all 3 dimensions. But again, we could check, right, how many things are attached to it. This has a central atom in one spot, and then 1, 2, 3, 4 things. So if you have 4 things connected to your central atom, you're trigonal planar. Sorry, you're tetrahedral. If you're 3 things attached to your atom, you're trigonal planar. If you're only 2 things attached to that central atom, you're linear. So you can kind of count what's connected there, see how many things are attached to your atom, and that'll give you an idea of what that shape is going to be for that. And we can do that for any time we do a Lewis dot structure. This is just kind of showing, right, the Lewis dots versus if you were to look at these atoms in kind of 3-dimensional, right? 1 atom with 2 things on either side, 1 atom with 1, 2, 3 things. This shows the 3D a little bit better. And if we go one more ahead, I try to rotate, but no, didn't work. So, so there's a little bit of rotation, but you can kind of see how this is really flat. This really does, these 2 stick back, those 2 stick out. So that kind of shape for those molecules is there. So this is very flat, this is very flat, this is 3-dimensional. So these atoms have different shapes when you look at those atoms in different angles. And then this is great when we have atoms that have all the atoms that are present, right? Hydrogen, carbon, nitrogen, oxygen. We don't have any single atom electrons on that central atom, but sometimes we do. Sometimes we get something more like H2O, where we have an H, an oxygen, another H, and we have extra electrons on that middle atom. So if you have extra electrons on that middle atom, you can still do these types of models too, but you get something that looks a little bit weird. So carbon here with 4 hydrogens attached to it, we got 4 bonds. 1 bond, 2 bonds, 3 bonds, 4 bonds. You could also do that for nitrogen, right? This nitrogen we could draw the Lewis dot structure of. We've done this one a few times, right? Nitrogen's got 5 dots normally. 1, 2, 3, 4, 5. We bring in a hydrogen with 1 dot, we form 1 bond. Bring in another hydrogen, bring in a 3rd hydrogen. And this nitrogen's cool. It's nice. Nitrogen's okay. It's got 8 dots around it. 6 dots are coming from the hydrogen shares, and 2 dots are not dots that the nitrogen brought on its own, that the nitrogen already had. So the nitrogen brought 2 dots of its own, but those dots actually take up space around the nitrogen. And even though we can't see them, it's like you have another thing bonded there. It's just something bonded there that's invisible. And the same thing for this water here. You have something that's bonded here and something that's bonded here that's invisible. So if you were to count how many things are attached to all 3 of these atoms, or all 3 of these molecules, this one, there's 4 H's. This one, there's 3 H's and some electrons. But if we were to count that, we'd say there's 1, 2, 3, 4. So even though those electrons are invisible, those electrons can't be seen, it's like you have 4 things there, just like you have 4 things here on this atom molecule set right here. And even over here, we have 1, 2 visible things, and 3 things, and a 4th thing that are invisible. So all 3 of these molecules have 4 things attached to a central atom. It's just some of those things are easy to see, and some of those things are not so easy to see. But they still all have 4 things, and they still have a tetrahedral-like shape. They still have that shape of a tetrahedral, except when you look at water, you can't see 2 of them. So it doesn't quite look the same as this tetrahedral molecule over here, but it still has that same shape. It's got that one thing in the middle, and it's got one thing sticking up, one thing coming out nice and thick, another thing coming out nice and thick this way, and another thing behind it. The only problem is that you don't see the thing over here or over here, but you still get this kind of shape. It's not a linear shape like you would if you only had 2 things attached. It's still at an angle. It's just that the electrons are in those other 2 spots. And we can kind of see that with this here, right? These are all those tetrahedral type shapes. except there's electrons in some of those spots. There's electrons in none of the spots here. These are 4 atoms attached to that central atom right here. But if I covered over this one, you'd get something that sort of looks like this. And if I were to cover over that one and this one, you get something that looks like this. And this is really, really, really different looking than a linear molecule, which would have one thing here, one thing here, and one thing here. And this would be 180 degrees. Versus this here is only about 110 degrees. So this angle here shows that even though there's only 2 atoms attached to this molecule, it looks different than something that only has 2 atoms attached to that molecule and nothing else. So if you do have lone pairs of electrons, they still count when you're trying to figure out the shape of that molecule. So for all these molecules here, there's 1, 2, 3, 4. 1, 2, 3, 4, counting those pairs of electrons, and 1, 2, 3, 4, still counting those pairs of electrons. These are all tetrahedral molecules, but sometimes they'll call these other ones bent. So you may hear that this is either a tetrahedral or a bent molecule. So you may hear water is tetrahedral, or you may hear that water is bent, but water is not linear for that. So those are kind of ways of kind of describing those. And water is not linear because it doesn't have a 180-degree angle. It only has that 110-degree angle. And it only has that 110-degree angle because the other 2 spots on the water are being taken up by those electrons. So that pair of electrons on the water over here and that other pair over here make it have 4 things around it. So we can kind of figure out the shape of any molecule, including ones that have extra pairs of electrons on the center. So being able to do Lewis dot structures, being able to figure out the shape of that molecule, the structure of that molecule based on the dots. And to do that, we would just go to our periodic table. And we kind of say, all right, are we in the 1 dot club, the 2 dot club, the 3, 4, 5, 6, 7, or 8 dots, right? How many dots do we put around the structure? We start putting the molecules down there. We start putting the molecules together. We start connecting the dots. And we start making shapes like we get here. We get a shape like this. Or if we have 1 dot left over, get a shape like this. Or even like that there. And these can get a little complicated over time so as you start adding more and more molecules, right? So this is an S with some oxygens. And we see that this only has 3 things attached to that central sulfur, right? If we cared about, in terms of this sulfur, how many things are there? There's an oxygen, there's another oxygen, and there's a 3rd oxygen. And there's no dots on this S, so we don't have to count anything else. Same thing for this molecule. Maybe they want to know about this carbon here, and they say, all right, there's 1, 2, 3. Maybe they care about this carbon instead. And then you would say, all right, there's 1, 2, 3. So always look at what they're asking for. They don't care about the chlorine, but maybe they do. And then there's only one thing. So depending on what they're looking at, but these molecules can kind of form some interesting shapes depending on how they come together. But we can always figure it out the same way by kind of looking at the structures, looking at the molecules coming together. So just like this molecule here, right? CO2, carbon in the center, the C is in the middle. So we're going to put C in the middle, and we're going to put the oxygens on either side. And we'll figure out the shape and the structure of this molecule. Figure out, is it linear? Is it bent? Is it trigonal planar? Is it tetrahedral? What kind of shape do we have going on? So carbon is in this row right here. Carbon's in the 4 dot club. Oxygen is in the 6. So C had 4. O had 6, the other O had 6, so 10. So there should be 16 dots total when we're done with this. And what we can do is we can just start putting the original dots that were there first, right? Carbon only has 4 to start with. Oxygen has 6. 1, 2, 3, 4, 5, 6. Oxygen has 6. So that's kind of our starting structure there. 1 oxygen with 6 dots. Another oxygen with 6 dots. They told us carbon was in the middle, so we put that there. And carbon's only got 4 dots. So if we wanted to do like the connect the dots method, we could do that. And we'd say, all right, let's connect the dots here. This is 1 bond. Let's connect the dots here, 2. That's a bond. All right, so oxygens now, it's got 7 out of 8. Carbon's got 6 out of 8. Oxygen's got 7 out of 8. It's not quite right where we want to be. Are there any more dots we can connect? Well, there's one pair of dots right here. So we'll do that. So this dot connects as well. Now we got 8 dots on this oxygen here. We got 7 dots on that carbon. There's one more dot we can connect over here. So now we got 8 dots here and 8 dots here. So now everyone's happy. Everybody's got their 8 dots, right? 2, 4, 6, 8, 10, 12, 14, 16. Still got 16 dots. We didn't lose anything. That's good to do. And we could just clean up the molecule and say, all right, well, let's just kind of draw this a little bit nicer looking. Oxygen, double bond, carbon, double bond, oxygen. So this is the same thing we had before, 6 dots, 8 dots. So everybody's still there. 1, 2, 3, 4, 8, 2, 4, 6, 8, 8. So everybody's got their 8 dots. And now we can figure out what's the shape of this molecule. Well, in terms of carbon, carbon's in the middle. There's 1 atom on the left, and there's 1 atom on the right. So 2 atoms total connected to a central atom. That's a linear type of molecule, right? Linear is when you have 2 things. Tetrahedral is when you have 4, and trigonal planar is when you have 3. So we're in the linear structure there. So this would be a linear CO2 molecule. Molecule of CO2 is a linear shape. It's flat. It's not 3-dimensional. It's kind of just 2-dimensional there, just a straight line. And we could do that for any atom that we're working with, any molecules we're working with. We could just go through our periodic table and figure out what atoms we're working with, what atoms are present, right? These were both, just to start with this, right, was C and O. These were both in the non-metal section. So if this was a metal, non-metal pair, we wouldn't even have to do this. If it was something like LiO instead, so maybe this was Li2O, then we don't have to worry about it because lithium is a non-metal, or is a metal. Metal, non-metal pairs are ionic compounds. We don't have to worry about 3-dimensional structures or shapes for those. So always check that it's a metal, non-metal pair versus 2 non-metals. If it's 2 non-metals, you can go on and do the Lewis dots. You can go on and do the structures. But for something like LiO, Li2O, that would just be an Li plus. There'd be a minus 2 oxygen. And there'd be another plus oxygen here. That would be our kind of molecule that we're working with, right? We have positively charged lithiums because they're in the +1 column right here versus the +2 column. And then over here, the 0 charge, the -1, the -2, right? Lithium's in the -2, +1, oxygen's in the -2. So if you're working with metal, non-metal pair, you don't have to worry about the shape and the structures. You just have to say, all right, is it charged? Does it write the formula? But if it is 2 non-metals, then we'll have to do the dots. We'll have to see, is there any bonds? Maybe this question asks what kind of bonds are present, right? There's a double bond between oxygen and carbon, and there's a second double bond between the second oxygen and the carbon. So maybe it asks you about the bonding type. Maybe it asks you how many unpaired electrons are on each atom. The oxygen's got 4 atom electrons around itself as unpaired. The carbon's got none. It's all bonds. The oxygen over here also has 4 unpaired electrons as well as 4 bonding electrons. So a couple of different things they could ask you about for that when we're looking at that. And you can do this for all sorts of different atoms, right? We did it for a CO2 molecule. We saw what shape we had. We'll do one more. We'll do it for this NF3 molecule, right? So NF3 is also a molecule. Let's just double check, right? Fluorine's over here. N is over here. So 5, 7. So these are the 7, right? If we were checking before. So these are the 5 and the 7 dot atoms. So nitrogen is going to have 5 dots around it. Fluorine's going to have 7. And we're going to try to get to the final number. 7, 4. So it's 21, 5. So there should be, in the end, 26 electrons when we're done with all our dots. 5 from the nitrogen, 7 from 3 fluorines, each giving you 21. So when we draw this, we should still have the same number of electrons. So if we were to draw our nitrogen, which they said is in the center, and we'll put 5 dots around that one first. And then we'll put our fluorines in too and give them their 7 dots. And then we'll do the last fluorine and give that its 7th dot too. So that's our starting framework, right? Fluorine contributing 7 dots, fluorine contributing 7 dots, fluorine contributing 7 dots, and a nitrogen contributing 5. But everybody wants to get to 8. So this fluorine can get to 8 by sharing with this nitrogen. This fluorine can get to 8 by sharing with this nitrogen. And this fluorine can get to 8 by sharing with the nitrogen too. So now fluorine's got 8. It's got 6 of its own and 2 that are being shared. Same for the other 2. And the nitrogen's got 2 of its own plus 6 that are being shared. So it's also got 8. So if we were to kind of figure out what shape is this molecule here, again, we'd want to count how many things are attached to that central atom. The central atom right here is nitrogen because that's the one in the center. So what's on this nitrogen? Well, there's 1 fluorine. There's a second atom here that's also a fluorine. There's a third atom that's also a fluorine. And there's these lone pairs of electrons. So that's a 4th thing as well. So this would be a trigonal planar shape as well. So you'd have 2 electrons sticking up here, and then these fluorines kind of coming out at different angles. This one's probably sticking back a little bit. This one's kind of wedged outward a little bit. So we would have a trigonal planar type of molecule here. Oh, sorry, not trigonal planar. We'd have a tetrahedral shaped molecule here, or you could say it was a bent molecule if you wanted to, because it's missing the electrons. These electrons aren't very visible. So it would kind of look, it wouldn't look like a flat triangle. It would look like a bent triangle that somebody kind of grabbed the middle of and lifted up. So just like if you go to your bed and you were to grab the sheet in one spot and pull it upward, you would get that same kind of shape where the bed would still be hanging onto the fluorines and the nitrogens where your fingers are kind of pinching up the sheet there. So this is not flat. It's not a flat triangle shaped molecule. It's a 3-dimensional molecule with some height to it. So it's got this triangle on the bottom, but the nitrogen is raised up. The nitrogen's not in line with the 3 fluorines there. So this would be either a bent or a trigonal, bent or a tetrahedral type of molecule based on that kind of structure. But again, you can answer all sorts of other questions too. This is a metal. There's no metals here. It's all nonmetals. The fluorine's got 6 lone pair electrons in a single bond. The nitrogen's got 3 single bonds. Nitrogen's got a lone pair of electrons. A couple different things it may ask you about as we kind of describe this atom here. So we could figure this out for any of these types of atoms as we kind of go through all the different shapes and all the different structures. But again, when you're doing this, just look at the atom, see where it is on the periodic table, how many dots should it have. It could have anywhere from 1 to 8 dots because we skip all the ones down here. So we kind of count based on those columns there, what dots we expect. So we can kind of look at our periodic table, see how many dots we would expect to see. We can look at our periodic table, see do we have metals versus do we have nonmetals, right? Nonmetals are on the left, metals are on the right there. So you have the metal nonmetal pairs. If you have a metal nonmetal pair, you just figure out your charges and you're done. But if you have 2 or more nonmetals, then we got to do these other molecules instead. And this was a pair, 3 nonmetals. This other one had 4 nonmetals. 2 of them were the same, 3 of them were the same, right? There were a bunch of fluorines and nitrogens, but there were multiple nonmetals paired up with this molecule up here. So that's kind of what we can do. We'll finish this up next time, which is a couple more examples of that, but this is almost the end of this chapter. So we're almost at the end of chapter 2. We'll be on to chapter 3 next time as we kind of do this some more. But as we kind of finish up, we'll do a few more shape practices and then see how does like polarity affect